This lecture explores fundamental techniques for working with text data, which is essential for many applications like natural language processing and sentiment analysis. We will cover one-hot encoding, word embeddings, and how to combine these techniques for practical use. The journey begins with one-hot encoding, a method to convert categorical data, including words or characters, into a numerical format suitable for machine learning models. At the word level, for a vocabulary of size V, each word is represented as a vector of V zeros with a single one at the index corresponding to that word. For example, in a vocabulary of the cat, sat, the would be represented as 1, 0, 0. Similarly, one-hot encoding can be applied at the character level. For an alphabet of size A character is a vector of A zeros with a 1 at its specific index. For instance, with an alphabet of A, B, C, A would be 1, 0, 0. Our first code example demonstrates character level 1 hot encoding. It loads a small subset of the 20 newsgroups dataset, specifically text about atheism and Christianity. It then takes the first document from this dataset and displays its initial 100 characters. A vocabulary of all unique characters found in the dataset is created, mapping each character to an index. The code then one-hot encodes the first 10 characters of the sample text, showing each character as a sparse vector, where a 1 indicates the presence of that character at its unique index within the character vocabulary. The output includes the one-hot encoded matrix and its shape, illustrating that 10 characters are represented across a dimension equal to the total number of unique characters. Moving beyond one-hot encoding, we delve into word embeddings, which offer a more sophisticated way to represent words. Unlike one-hot encoding, which treats each word independently, word embeddings represent words as dense vectors in a continuous space, where words with similar meanings are positioned closer to each other. This captures semantic relationships. Popular techniques for learning these embeddings include word2, vec, glove, and fasttext. The next code cell prepares the environment for using word embeddings. It installs the GenSim library, which is a popular tool for topic modeling and word embedding, and then downloads and unzips pre-trained glove embeddings. This step ensures that the necessary libraries and data are available for further exploration. Following this setup, the subsequent code block loads the pre-trained glove embeddings, specifically the 50-dimensional vectors. Once loaded, it demonstrates two key capabilities of word embeddings: finding words semantically similar to a given word, such as king, and performing word analogies like king minus man plus woman. The output lists the words most similar to king with their similarity scores and then presents the results of the analogy, showing words like queen and princess as the closest matches, along with their scores. This illustrates how embeddings capture complex relationships. Next, we outline a general workflow for natural language processing tasks. This typically involves loading raw text data, followed by pre-processing steps such as lower casing, removing punctuation, tokenization to split text into words, removing common stop words, and stemming or lemmatization to reduce words to their base forms. After pre-processing, text is vectorized using methods like bag of words, one-hot encoding, or word embeddings. Finally, this vectorized data is used to train a machine learning model for specific tasks like classification or sentiment analysis. The final code example demonstrates a practical text classification workflow using scikit-learn. It loads the 20 news groups dataset and creates a machine learning pipeline that first applies a TF-IDF vectorizer to convert text into numerical features and then uses a multinomial naive Bayes classifier. The model is trained on the training data and then used to predict categories for the test data. The output displays the model's accuracy, showing how well it performs. Additionally, it provides predictions for two new sentences, God is love and atheism is a belief system, correctly classifying them into their respective newsgroup categories. In conclusion, this notebook has covered fundamental concepts for working with text data. We've seen that one-hot encoding provides a sparse representation useful for smaller vocabularies or character-level tasks, while word embeddings offer dense, semantically rich representations that capture intricate relationships between words. The importance of preprocessing text data before vectorization was highlighted, and we observed how vectorized text data forms the basis for training various machine learning models in natural language processing.